Well, thanks for coming to Space Place tonight. It's our second Tuesday when we normally have a guest presentation, so I'm not really a guest since I'm the director here. But I did want to use one of these opportunities to talk about a special topic, which many of you who are familiar with Space Place will understand has been a sort of a standard, a stalwart of our exhibits in here, of our exhibits of spacecraft hardware, things that have actually flown in space. One of the most interesting ones has been what we call WUPPE, and so I want to explain why it's not there anymore and what is happening to it. WUPPE is the instrument that you see here outlined. It's one of a package of 3 telescopes that are there, and WUPPE is sometimes a little hard to pick out. Here it is in the cargo bay of the space shuttle. The cargo bay of the space shuttle right here, and WUPPE is outlined, is marked up here so that you can see it. It's got this sort of boxy sun shield, and the body of it is here, and it's got this kind of radiator panel. Those are all shiny surfaces, mirror-like almost surfaces. So what you see them doing is reflecting the blackness of space right there. That's why they kind of fade into the background, these big black areas here. So this package, of which I'll talk more about what constitutes this package here. This package, including WUPPE, flew on 2 space shuttle missions in 1990 and then again in 1995. And so it spent a good bit of time in space doing astronomy aboard the space shuttle back in the days when we flew space shuttles. The package that WUPPE is part of is a package of ultraviolet telescopes, and they were part of a payload called the Astro observatories. That's why you keep seeing Astro all the time. That's not that's the actual name of the package. A package of ultraviolet. I'll be saying ultraviolet so often that it's just UV most of the time here, of ultraviolet telescopes. Of course, ultraviolet radiation doesn't make it, most of it anyway, doesn't make it through your Earth's atmosphere, which is a good thing for us down here on the surface. We don't need that. But astronomers like to see what ultraviolet light is emitted by celestial objects. Ultraviolet astronomy, in effect, can only be done in space. So the Astro package was made up of 3 ultraviolet telescopes. One of them was called HUT, which stands for the Hopkins Ultraviolet Telescope, and it of course came from Johns Hopkins University. One was called UIT, which stands for the Ultraviolet Imaging Telescope, and it was built by the NASA Goddard Space Flight Center, which are one of NASA's primary sites for space instrumentation, Goddard. And so UIT came from there, and then WUPPE came from Wisconsin, of course, and WUPPE stands for the Wisconsin Ultraviolet Photo-Polarimeter Experiment, and it was built right here on campus at our own space astronomy lab. The acronym itself tells you a couple of things. It tells you it's from Wisconsin. It also tells you that it is a polarimeter. That word doesn't show up in these other instruments. Polarimetry is a rather specialized part of astronomy. And the experiment word is significant too, because polarization studies in the ultraviolet were, it was basically unknown how well the instrument would work and what you would see. So there was a whole lot of let's just try this and see what we get when we try to do ultraviolet polarimetry. So those 3 telescopes, HUT, UIT, and WUPPE, are all bundled together there in this package that fits in the bay of a space shuttle orbiter. So what is this polarimetry thing? Polarimetry, polarization, is a property of light, and it's one of the things that we have to specify to fully describe light. Most of the light that we experience around us is unpolarized, which really means that it's a mixture of all possible polarizations. But polarization of light is it's a property of electromagnetic waves, and so you can talk about it in terms of light or radio waves or ultraviolet or whatever. They all have polarization, and it comes down to the physics of a wave of light, of the wave description of light. So here you see a plot of the electric field. So a light wave is a combination of an electric field and a magnetic field. That's classical electromagnetic theory. And generally, we talk about the plane, the orientation of the electric field. And so when we talk about polarized light, we're usually talking about polarization as measured by the electric field. So for example, here's a polarized wave, light wave, in which the polarization is aligned with, this is the z-axis here, if you can read that. So this wave is polarized along the z-axis. This is a polarized wave. But if you have a lot of these things that are all mixed together, like here we have many waves coming out of this light bulb, it's just random what the polarizations are. It's a mixture of all of them. Here it's unpolarized. We would call that unpolarized just because it's a mixture. But you can do things like put a Polaroid filter. There are a number of kinds of substances that will do this. The most common is plastic polarizing sheets that basically they make sunglasses out of. You can put a polarizing filter in there, and it will block all but, in this case, the vertically polarized rays. So it blocks all of these others. So on this side of this polarizing filter, this light is polarized over here. Well, of course, that's being done then artificially. We could do that right here with a light source and some Polaroid filters. But there are natural phenomena that will polarize light as well. And so that's what's interesting here. So to give a very terrestrial example, if you have, say, unpolarized sunlight that reflects off of, it says air and glass here, but that could also be water. If it reflects off of the surface of water here, that reflection will polarize the light partially at that point. And so if you're over here, the reflection that you see a spot of glare on whatever surface this is, the water or the glass or the ice or whatever it happens to be. And since it's polarized, by making your sunglasses out of a sheet of this polarizing stuff, you can block that glare. You can attenuate that glare, and that's what Polaroid sunglasses do. They take advantage of this, process here to reduce glare sources, whereas unpolarized sources are not as attenuated by the Polaroid sunglasses as glare is. So it happens all around us in nature all the time. It tends to happen on Earth by means of scattering and reflection. So astronomical polarization can happen too and can tell us some interesting things. That is to say, light from astronomical sources can be polarized and can tell us some interesting things. But it's a relatively recent, as these things go, it's a relatively recent study. The first real astronomical polarimetry didn't really get started until the late 1940s. And it's an outgrowth of astronomical photometry, of specifically photoelectric photometry, which actually was pioneered here at the University of Wisconsin. But instruments were then adapted basically by taking a photoelectric photometer and then putting some kind of polarizer in front so that you can rotate it and you can see whether the astronomical light that you're getting exhibits polarization, and maybe that tells you something. So the pioneers of this work were at Yerkes Observatory and at the U.S. Naval Observatory, Albert Hiltner and John Hall, respectively. Hiltner actually learned to do photometry from Wisconsin astronomers working there at Yerkes. Yerkes and Washburn collaborated a lot on exploring the applications of astronomical photometry, and Hiltner started working with polarization studies there. And Hall, Hall was one of the early pioneers of photoelectric photometry as well. So what they found was that if they studied stars, if they looked at stars with their polarizing photometer, that they would find that on the average, there were certain polarizations in certain parts of the sky, that starlight was polarized in certain parts of the sky. And they concluded that what they were seeing there was that the light from the stars itself is not intrinsically polarized in general for a typical star, but as it passes through the interstellar medium, it passes through a scattering medium that's known to be out there, called the interstellar medium typically, which consists of gas and particles. The gas doesn't polarize the gas, but the particles do, and the particles are typically not round, but extended, presumably. And so they tend to be aligned by the galaxy's magnetic field on the average. And so the preferential alignment of these particles along the magnetic fields of the galaxy produce regions of polarization. So you look at different stars in different parts of the sky, and you see, in effect, you're seeing the effect of the galactic magnetic field. So this was the earliest form of polarization, but they're of course working in the visual with ground-based telescopes, looking at visual wavelengths. But this kind of effect, scattering and polarization, ought to be stronger as the wavelength gets shorter. So it ought to be stronger in ultraviolet, but you can't find that out unless you can build an instrument to put in space. So putting this kind of instrument in space to see what effects we can find of polarization in celestial objects, that was the key, that was the motivating factor behind building WUPPE. So what do you expect to see? Well, there are a number of effects, that some of which were hinted at in the visual, and some of which are much clearer in the ultraviolet. But polarimetry can reveal a number of things that you can never see directly in your telescope, or at least extremely rarely. So for example, the shape of a star. We never see, except for very, very few cases, we don't see stars as a disk. But suppose there's a star that's rotating very, very rapidly, so rapidly that it is, that its rotation makes it into an oblate spheroid, so that Jupiter actually is slightly oblate because of its rotation. It's bigger in the equator than it is around the poles. So is the Earth slightly. But rapid rotating stars, this effect can be extreme. In that case, you would expect, because the light from around the edges of a star should be polarized, but a perfectly spherical star, we should get an even mixture, and the overall light from the star should be unpolarized. But if it's spinning rapidly around along its equator, then we'll get more polarized light from the parts of the star that are extended out and are moving fastest towards us and away from us. So by measuring polarization of some stars, we ought to be able to see the ones that are rapid rotators and see the distortion of the actual body of the star. That's one application. Another application of polarimetry is when you have interesting structures around stars. So things like bipolar outflows and disks. So I've given an example here. This is a protostar. So deep inside this circumstellar disk, there's a star inside there. And this light that we see is scattered starlight. Starlight that's emerging from the star and then being scattered towards us. Emerging from the star, maybe going off in this direction, but then scattered towards us by the matter in this disk. This light should be polarized. And similarly, the bipolar flows should be polarized. So now in this case, this is a Hubble image of a circumstellar disk, which is amazing in itself that we can now get pictures of some of these things. But there's an awful lot of these that are still too far away for us to actually see in a telescope. But if you look at a star like that and measure polarization that matches the models for disks and bipolar flows, then we can find what stars may have circumstellar disks by the polarization around the stars, not by imaging them directly. So it would give access to a lot, many, many more examples of this kind of thing. And we find jets and disks in lots of different astronomical situations, not just protostars, not just new stars and forming solar systems, but in, say, highly evolved binary star systems. For example, over here, where we have maybe a white dwarf and matter is flowing from this extended red giant here, this bloated red giant. Matter is flowing onto this white dwarf star, and there's a circumstellar disk around there and a bipolar flow. That's going to produce lots of polarization signatures. So again, you can look at this sort of thing and a situation like this and determine certain things about the structure of the system strictly from the polarization. This is an artist conception here. There's almost none of these sorts of things that we can image directly. And then again, back to the original problem that Hiltner and Hall were working on, the interstellar matter. You can, by the nature of the scattering of these dust grains that produces that polarization tells you something about the dust grains. And so looking at the character of the polarization can tell you about the orientation and the size, and to some extent maybe even the composition of these interstellar dust grains. So there can be a number of applications, all these sort of very special cases that polarize light that were potential targets for WUPPE. So NASA settled on the idea of building this package for these Astro payloads to do ultraviolet astronomy. The instrument concept was based on something else that NASA had developed called Space Lab. So Space Lab was developed as a collaborative project between NASA and ESA, the European Space Administration, which, that is Space Lab, was designed to fit into the cargo bay of the space shuttle and take on a number of configurations to support scientific operations in the cargo bay. So a common one was they would actually have a sort of a habitat, sort of a lab in there that allowed extra space where the astronauts could actually work, a shirt sleeve environment that expanded the available space in the shuttle, so you could have labs there in the space lab. But very important to the whole, but that was actually optional, the structure, the so-called pallet structure, and then all of the infrastructure that goes in, providing power and communications, and in the case of astronomical payloads, a pointing system. Those were all parts of Space Lab as well. So the Astro payloads were designed to work within the context of this Space Lab infrastructure and environment. Well, one of those telescopes, of course, was built here at Wisconsin, the polarimeter, WUPPE, in part because here at Wisconsin, we have deep experience here in ultraviolet astronomy. We're one of the places that has pioneered this, going all the way back to the 1960s with the Orbiting Astronomical Observatory, where we built some of the first successful orbiting ultraviolet astronomical instruments. And also we had flown lots of suborbital rocket instruments, which were also ultraviolet astronomy. So that led to the Space Astronomy Lab receiving a contract to build an ultraviolet polarimeter, which became WUPPE, in 1978, which was the same year that another instrument that's also on display here at Space Place, the high-speed photometer, which flew on the Hubble Space Telescope. That's the same year the Space Astronomy Lab received contracts for both of these major things. In the same year, 1978, it entered a very busy epoch for the relatively small Space Astronomy Lab. We're not aerospace contractors here, we're a small astronomy department. So WUPPE, though, was designed and built entirely on campus and delivered to NASA, where then it was combined with these other instruments into the pallet and onto the pointing system, and was delivered in time for a launch for the first mission, which was scheduled in March 1986. Here you see this picture here shows a sort of plywood and cardboard mock-up. This is one of the earliest, maybe the very first mock-up of the instrument, so very early stages there for sort of a crude engineering model that you could use to begin thinking about where you put your optical components and where you put the electronics and what needs to be heated and what doesn't. And that guy standing back there, that's astronomer Ken Nordzik, who was one of the principal designers, really the principal designer of the instrument, and we'll see more pictures of Ken as we go along here. For instance, here. So the primary team of astronomers included Ken Nordzik, here he is, right here, along with Art Code, Dr. Arthur Code, who was also the director of the Space Astronomy Lab and very prominent, internationally known astronomer. Here he is, here in the middle, and Chris Anderson, another UW astronomer, right there. You can usually pick Chris out because of that bow tie. And Karen Bjorkman, Dr. Karen Bjorkman, another UW astronomer. They were the core scientific team for the design and the construction and then the operation of WUPPE. Ken, I need to note, actually was applied for and was selected for a position as a payload specialist to fly on the Astro missions. One of NASA's goals with this Astro mission was to build a payload that would actually be operated in real time in orbit by astronomers. The thinking being that you could, the outcomes were so unexpected that the thinking was you might want to be modifying your observing plans sort of in real time based on interpreting the data that you're getting right now. So basically you need some astronomers to be looking at that and thinking about those, the next steps in operations. So Ken was selected as one of those and was actually on the crew in the sense of being one of the backup crew for the first Astro mission. In addition to these principal scientists here, there was a large team. You don't build something like this with just a handful of people. It takes a lot of people in different skills, engineers of all sorts, computer specialists of all sorts, and managers. You're keeping track of every nut and bolt that comes in and goes out because WUPPE was being built to fly on the shuttle. And if you're building something to fly on a manned spacecraft, all the standards just go off the charts for what you have to, the bookkeeping and the attention to detail that you have to deal with. So as I said, between 1978 and when WUPPE was delivered in the mid-1980s, in time for the scheduled launch in March '86. However, this is where fate intervened because the shuttle launch before the Astro 1, the scheduled Astro 1 mission in March of '86 was the Challenger in January of 1986, which was, of course, a major disaster at launch. And the result of that was that shuttles were grounded and the shuttle manifest was completely reworked by NASA. In fact, the total number of shuttle missions was backed off. And in the case of the Astro missions, which had originally been scheduled for as many as 6, they were cut back to 2, which is why we're only talking about Astros 1 and 2. In practical terms, all of that stuff, here we have Ken again. This is the actual cargo bay of the shuttle down there at Kennedy, and this is the Astro payload right here, and we're looking at the bottom of it, the back of it. The telescopes are all pointing out this way. This is the pointing system, the instrument pointing system right here, which couldn't lift this instrument when it's on Earth, but when it's in orbit, this would be the thing that can pick up the whole package of instruments and point it with great accuracy anywhere in the half of the sky that is looking out of the cargo bay of the shuttle. So the instruments, though, had to be taken back out and put into storage, and there were some, it turns out there were some major consequences of just this grounding for 4 years as these instruments had to go into storage. They had to be kept theoretically in flight conditions because all these are built, under clean, highly controlled conditions, and maintaining that storage actually led to some problems along the way. So 4 years in storage until finally the Astro missions were ready to fly in December of 1990. It was Astro 1, which flew on the Columbia. And as I mentioned, there were some problems during this flight which led to a dramatically reduced science output. For example, in the case of the control electronics, this tells you how much the scientific instruments depend on just everyday support electronics. There were computer terminals inside the shuttle that, of course, were used to then control the equipment out there in the shuttle bay. Those had to be kept from accumulating moisture and things like that. So apparently their ventilation fans were kept running during those 4 years But then before flight, they should have replaced the dust filters, and they didn't. And so these things overheated once they were in orbit. And I heard that apparently there was actually a little bit of smoke at some point before they shut those down. A friend of mine says you can really get the attention of the flight directors if you say, we've got smoke up here. So they had to shut those down, and they had to operate those instruments by a completely different method from what was intended there. They had to develop workarounds on the fly. So this is a nice example of how having humans right there to interact with the equipment and react to situations can be a big advantage. Not the kind of situation you want to create, but it still yielded some good science. But the really productive flight then, not surprisingly, the second time you do this, a lot of things go better. And the Astro 2 was actually a very productive flight, very scientifically productive flight. So what kind of science did they do? Well, there were a number of firsts. The way to think about this, all of this ultraviolet mission, is that this was, especially with the polarimetry, this is largely a survey. And the first thing you always do when you have a new way of looking at the sky is, this happened, the radio astronomy had to go through the same phase as well. You look around and you start looking for the sources of the radiation and trying to categorize them. In this case, in many cases, they knew what they were pointing at, and this key down here tells you what sorts of objects correspond to these spots in the sky. These are stellar observations up here, but also star clusters or abnormal galaxies and so on. All these different categories of targets scattered across the sky that were, and this is only a sampling. This is actually not enough because I think there were at least over 200 targets taken. But it gives you some example, some idea here of the number of targets, which include, as I mentioned, these disk, jet, and magnetic fields, some of the very first UV observations, confirmations of bipolar dust flows, bipolar jets, rather, in a number of situations, measurements of the properties and particles in the interstellar medium, those rotating stars that I mentioned, mapping of the galactic magnetic fields. So this survey of polarizing sources was actually exploited a little bit later on. That is the survey from the WUPPE observations in observations by suborbital rocket experiments. But again, this polarimetry is a highly specialized sort of field, and very little of it has actually been done. There's a huge amount yet to be done in the science of ultraviolet polarimetry. But this phase of it ended with Astro 2 in 1995. At that point, the Astro 2 package was broken down into the component instruments. So we had the three instruments, the HUT and UIT and WUPPE. And I haven't mentioned the structure that but you'll see a picture of it here in a moment, the structure that they were all put together on, which was a thing called the cruciform structure, or just the cruciform, which was the thing that sits on top of that pointing system and has four quadrants that mount together the three telescopes, and then a celestial guidance system that looked at the sky and did star tracking in order to do refined pointing. So all of that equipment was broken apart. Those five major components were dispersed. And WUPPE came back here, came back to Wisconsin, where it was up at Chamberlain Hall for a little while with post-flight calibration, and then it went on display at Space Place, where it had been then ever since. So if we take just a step back here, when we're talking about the Astro payloads, and a good way to think about it, and this was pointed out to me by one of the lead figures here on what I'm about to talk about, the Astro Restoration Project, is that the Astro instrument package was an observatory, a space observatory, but it's an exception to the general pattern in that we get it back. All of the other great space observatories, the Hubble and the Spitzer, and this will be true of the Webb as well, those are never coming back to Earth. We take lots of pictures of them before we launch them, and then they take lots of pictures for us and send it back once they're out there, but we don't get those back. So the Webb will never be in the Smithsonian. But the Astro payload is an example of one that did come back because it was flown on the space shuttle. So it's a retired historic space observatory that we already have, but after 1998, when the Space Lab program was shut down as well, and all the pieces of it were dispersed, this great observatory went off in various pieces, WUPPE coming here, for example. So pretty soon after this retirement of Space Lab, a small group of NASA employees who had worked on the Space Lab project anticipated what would come to pass 20 years later and began collecting this equipment. So for example, the cruciform structure, which is a huge piece of milled aluminum, which was worth something as scrap metal, actually ended up in a scrap yard, but fortunately wasn't scrapped before they located it and bought it back from the scrap yard, and it sat in somebody's garage for 20 years. The instruments were a little bit easier because they were deliberately preserved by us for WUPPE and by the owners of the other two instruments, but a lot of that equipment disappeared forever along the way, and has part of what they've had to do is to track down substitutes for some of these things. So by 2020, this group many of whom had by that time retired and were ready to devote more time and resources to this project that meant so much to them from their days working at NASA, they formed something called the Astro Restoration Project. And the Restoration Project in 2020 partnered with a museum, the U.S. Space and Rocket Center in Huntsville, Alabama, with the intention that they would recreate the Astro payload there. And the Restoration Project also worked with the Smithsonian, and the curators at the Smithsonian agreed that the reconstructed Astro payload, which is still hypothetical, even still at this point, although coming together, would be a suitable acquisition for the Smithsonian to display there as an example of a major shuttle payload, as an example of a major space observatory at their space shuttle exhibits, which they have up there at the Air and Space Museum. So in 2020, this path began to emerge of reintegration, reacquiring pieces, reintegrating, restoring the payload to museum quality, and then ultimately going to the Smithsonian. So ARP is an educational nonprofit. You can find it here at this website if you want to see a little bit more about what they're doing. And they even accept donations, tax-deductible donations to their work, which is all privately funded by donors and these enthusiasts here who are putting lots of their time and a fair bit of their money into this. So what do you have to do to reunite these telescopes? Well, in the case of WUPPE, it was fairly straightforward because WUPPE was here, and we had preserved most of the handling equipment. These things all have specialized handling equipment. We had preserved most of the handling equipment at a storage site that we have. On the other hand, the telescope that had ended up at the Smithsonian had been transported there on its handling equipment, and then the handling hut, and then the handling equipment had been sent back to Hopkins. So those two things were separated, and they're still looking for, last I heard, they're still looking for the handling equipment for Hut. If they can find it, good. If they can't, they have to build a replacement. But in the case of WUPPE, here's one of the major handling fixtures that we had cleaned up and pulled out of storage. So this was actually happening last summer of 2021. There was a lot more to it, but this is the biggest, heaviest piece, which actually holds WUPPE so that, and you'll see this operation in a minute, so that it can be rotated and then lifted out and then mounted into the cruciform, all of which had to be done for flight, and so also has to be done for restoring the payload. This big box over here contains something that you never saw at Space Place, which was that big square sun shield that was outlined there on that first picture I showed, because we didn't have room to exhibit it here at Space Place. So it stayed in this shipping crate in storage as well. but that has been reunited, and you'll see it in a moment. So summer of 2021, we had to spend a couple of weeks digging out, cleaning up this equipment and getting it ready to be shipped. And then we had to get WUPPE ready to ship as well. And so here you see the whole mess being loaded at the loading dock of Space Place, just upstairs here. That's WUPPE wrapped up in plastic there and on its little home, actually locally made dolly, not a proper handling fixture, but that's how we had it mounted on display all these years. And back in here, there's the sun shield back in that crate, and that's this handling rotating fixture right here is back in here. So this all got loaded up in September, finally, of 2021, and shipped off to the U.S. Space and Rocket Center at Huntsville. So the actual climax of this part of the operation came along last February, when all the equipment was there and all the preparations had been made. WUPPE is actually the first of the instruments, the first of the three to arrive down there, and it's the first to be integrated back onto this cruciform thing that I mentioned. This is the cruciform structure back here. So this is milled aluminum, although it's covered with thermal fabric here, and there are mounting points here and here. So here you see WUPPE standing vertically. It would have been shipped horizontally in this frame here and then pivoted up to vertical. And then there's a lifting fixture, which is this shiny thing here, that allows you to lift the telescope out of this fixture and over onto here, which is what you see happening right here. This is the lift team at Huntsville. And they're actually lifting it up for flight. They had these big cranes, overhead cranes down at Kennedy. But in this case, you'll see it in a moment. There's actually a forklift that's pulling the lifting fixture up, lifting WUPPE up, and it's being coaxed into this quadrant here of the cruciform, right back there. So these guys in yellow, they're the local lifting crew that were contracted in Huntsville to bring in the forklift and to do this heavy but very delicate lifting. And here you see in the white coats are the restoration project team members here. You'll see some more of them. So here's WUPPE having been mounted into the cruciform, and now it's got the sun shield installed up here too. The sun shield is quite light, but it had to be lifted up on there. So you see some of the restoration team members. These are all former Space Lab people, or in the case of Dr. Zellner here, an astronomer who was on the WUPPE team, and she's been working with the team there too. Here they are. That's Nicole again, and this is Scott Vangen, one of the instigators of this original Astro restoration process. So that's the cruciform right over there. This is a little model of the Astro payload of the Astro telescopes here, the Astro 1 payload. And there's the completed lifting operation with the Astro restoration team. Most of them in the white coats, except these people in the blue shirts here are also parts of the team. And they're getting ready the next lifting task. This was just after WUPPE was mounted up here. But the next task is the instrument pointing system, and by the next day they had it mounted up there too, because the instrument pointing system occupied this next door bay of the cruciform right over here. So this is sort of what it looks like now without the people at the U.S. Space and Rocket Center right now, where it's currently forming an exhibit. In fact, they've kind of made the restoration work into a living exhibit. You can walk by there and see the team members working on the restoration back there, and they'll be mounting in a similar way. They'll be mounting UIT and HUT back here in the back quadrants of the cruciform here when those things arrive down there at the Cape. I mean, at Huntsville. So this was all done last February, and the next steps are for HUT and UIT to be shipped to Huntsville. as I mentioned, they're problem solving constantly with these sorts of things, because some of the stuff still exists and some of it doesn't. The question of whether the hut handling facility can be located is still an open question. Reintegrate both of those instruments then onto the cruciform, and then spend basically the next 2 years getting it ready to go to the Smithsonian. The Smithsonian is not quite ready because they're in the middle of a major remodeling operation up there. So until they finish their remodeling, the whole Astro payload will be on exhibit in Huntsville until it's ready to go to this, until really the Smithsonian is ready for it to go to Washington, at which point then it should be installed out there and on exhibit in the Space Shuttle exhibit, where they have the Shuttle Discovery out there at the Smithsonian as well. And that is where then the current arrangement is that WUPPE is on loan to the USSRC, to the Huntsville Museum. And once it's all ready, then the university will donate WUPPE to the Smithsonian, so it'll become part of this permanent Smithsonian questions, part of the permanent Smithsonian collections. And we were talking about this a little bit earlier. That will mean a lot of things. It will mean a lot more people will see WUPPE up there, and they'll see it in the full context of the system in which it operated alongside its companion instruments, in the context of the Space Lab hardware, in the context of the shuttle orbiter, all right there at the Smithsonian. So Wisconsin's astronomical history will have a very prominent place up there. It won't be the only piece. There's other Wisconsin astronomy, pieces of Wisconsin astronomy at the Smithsonian already, because the University of Wisconsin has a long and important history in both space astronomy and, as I mentioned a little bit earlier, in photoelectric photometry. So the Smithsonian has a collection of photoelectric detectors that came from Wisconsin, for example, as well. So be one more step in the preservation of these things for educational purposes and for historical preservation. So I hope that answers the question, where has WUPPE gone? And I want to thank you very much for your time and attention here. And in just a minute, I'll be happy to take any questions or discussion about that. So thanks for coming tonight.